Hi, in this video I would like to do a review of exam 3. I'm going to walk through every exercise and we're going to solve them all. I did not necessarily expect you to solve every problem. Some of these were very difficult, but let's get right into it. So for the first exercise, you had to integrate the sum of the squares over this curve C parameterized by sine t, cosine t, and 8t as t goes from 0 to pi over 2, and the integral is with respect to ds. Okay, so first thing you got to do is take a derivative of your position vector. So the derivative of this is cosine t, negative sine t, and 8, right? So what is RT? RT is x, y, and z positions, okay? And when we do this integration, this is going to be the ds is going to be dx dt plus dy squared dt and dz dt squared dt, right? So this is basically the Pythagorean theorem for our curve. Okay, so let's just do it explicitly. So x squared, this is going to give us sine squared t, y squared, this is cosine squared t, plus z squared, this is going to give us 64t squared, and then we're going to use the derivatives, okay? We're going to use our derivatives. This is going to be cosine squared, so cosine squared t plus the square of sine, that's going to be sine squared t, so sine squared t plus 8 squared, which is 64. So you have 64 dt. Okay. Now, obviously, you know from experience that this is 1 and this is 1, right? Okay, yeah, I guess that's better. Right. So, what does this do? Well, I integrate this from 0 to pi over 2, because that's what was given. Okay, so this is 0 to pi over 2, 1 plus 64t squared. This is 1 and 64, so that's going to be the square root of 65, and then a dt. Okay, so we're just about finished with this first exercise. So this is t plus 64 over 3t cubed. You put in these parameters, and you should get 65, root 65 pi over 2 plus 8 thirds pi cubed, and this is about equal to 679.2. Okay, so that's pretty much it for the first problem. Very, very simple problem, just a little warm-up. Okay, so take a moment, pause there. Okay, good, let's move on. Okay, so the second problem said evaluate evaluate the integral f dr over segment C, where f equals 0, 0, -1, and we have this curve y equals 1/2 x cubed minus x from 2, 2 to -2, -2. Okay, so this is nothing too deep, okay? It's just this function right here, right? That little curve, right? So you literally go down and you travel like this, right? So you're starting off at 2, 2, and you're going to -2, -2. And the direction matters, right? So you're starting at, in terms of x, you're starting positive and you're going negative. So you're going to the right. And the particular shape is given by the curve. Okay, well, that's all fine and dandy. Let's do the calculation. So, even though we're in the xy plane, we can still use a three-dimensional vector to do the calculation. This is, I guess you could say, what we're more familiar with. So in this case, z is going to equal 0. So r of t is going to be x, because x is x, and then x is going to be 1/2 x cubed minus x, and then z is 0. Right? Now, so x should be t. So go ahead and replace all that with t. Right? So you could say x or t, but you just say let x equal t, and then if that's equal to y, then when you plug it in here, just replace every instance of x with y. Okay, so I'm going to take the derivative of this, and this will give me 1/3 t squared minus 1, 0. Okay, and now I'm just going to do the calculation directly. So by definition, f was 0, 0, minus 1. This was actually part of the problem, right? So 0, 0, minus 1 dot dr. Okay, and let's remember. Okay, let's remember what does this mean? Well, this is the integral frt dot r prime t dt. Right? So r of t is our parameterization for the curve C. Okay, so it's right here, and we have the derivative, r prime of t. Don't forget your dot product, right? So you had a dot here before, now you're transferring it to those vectors. Okay, so that means that, well, I'm going to go ahead and rewrite that 0, 0, minus 1, because notice that is a constant. That f is constant. So even if I plug in that rt and I feed it through that first, right, it doesn't really matter. It's like if you had the constant f of x equals 3, right? Does it matter what x is equal to? No. And does it matter how you get that x? What your position vector is? No, it does not matter. So the only thing we care about now is r prime of t. So I'm going to dot it with r prime of t. 1/3 t squared minus 1, 0 dt. Okay, and now I'm going to I gotta include the bounds here now. So I'm going to convert the c into 2 and minus 2. Now I got that because keep in mind that t is x, and we have this curve, right, that does this stuff, right? and x starts off at 2, and then it ends at -2. So I'm going to go from 2 to -2, okay? So when I do this calculation, I'm just going to get 0, right? The dot of those two vectors is just 0, so that's 0, and the integral of 0 is always 0. So nothing too complicated there. That was exercise 2. Okay, so the next exercise asks us to determine if certain vector fields are conservative or not. So let's find out. So part 3A, you have this vector field So we're supposed to find out whether or not it is a conservative vector field, and if it is a conservative vector field, we need to find the potential function. Okay, so the first one is not conservative. Let's find out. So one of the conditions, if this is P and this is Q, a necessary but not sufficient condition is that del P by del Y is equal to del Q by del X. So the way I like to remember that is I say the first with respect to the second equals the second with respect to the first. Okay, well, first and second mean different things in this context, but it's just like a catchy phrase to remember. Okay, so that's the necessary condition. So what is this derivative with respect to y? So it's -1 plus e to the x cosine y. Right? Very, very straightforward. What about the second one? Well, the second one is del Q by del x. This is going to be del x. I'm going to act on this, so let's simplify it. X e to the x plus 2 e to the x cosine y. Okay, and when I apply the derivative to the first guy, I get x e to the x plus e to the x, right? Product rule. And then when I apply it to the second one, 2 and cosine are both constant, so the only thing I take a derivative of is e to the x, and so I get e to the x cosine y. Now, let's look at this. So, are these two things, are they equal? Right? They're not equal in general. So the thing is, they have to be equal for every single value of e and x. So you just got to find one set of values that makes them not equal. Okay, so let's look at it for a second. How about if e to the x cosine y is equal to 0, then this is also equal to 0, and this is negative, but e to the x is always positive, so you're asking me to say that a negative number is equal to a positive number, so therefore they're not equal. Or more likely, you just say, oh, these are clearly not equal, but that's not quite right. You want to actually find at least one set of values, x and y, that negates this fact, okay? You actually need to find those values. It may not be immediately obvious that they're actually not equal. I mean, it is, but, you know, demonstrate it. Explicitly demonstrate it. Okay, so the next order of business, we're going to do problem 3b. So 3b, you have fxy equals y e to the x plus sine y e to the x plus x cosine y. Okay, so again, this is P, this is Q, if we take the derivative of the first with respect to the second, right, with respect to y, we get e to the x plus cosine y. And if we take it with respect to the second one with respect to x, we also get that. Right? E to the x, x cosine y, cosine y. So this is obviously conservative. Okay, so if it's conservative, what this means is that there's a little f such that this backwards e means there exists. Okay, so there exists f such that del f equals f. Okay, so why is that helpful? Well, what that says is that the derivative of f with respect to x is going to equal the first component, right? So just remember that this right here is del xf, del yf, okay? And I'm saying that those are equal, right? But this equal sign is true by definition, and this equal sign is true by the fact that it's conservative. Okay, so yeah. So these are always the same object, true by definition. Okay. So I'm going to take, I want to find f, right? The whole goal is to find f. And if you think back to your fundamental theorem of calculus, if you have a derivative, you can integrate it. If you integrate it, you get your, if you integrate a derivative, you come back to where you started. So what we're going to do is we're going to integrate this with respect to x, okay? And this is going to mean that we need to integrate y e to the x plus sine of y dx. Okay, so this is y sine ex plus x cosine y plus a function in terms of y. Well, I'm sorry, this should be sine. I copied that wrong. So sine y, yeah. So I'm integrating this with respect to x. And so you might say, well, where did this h of y come from? Well, the point is that if my f had another thing in here that is in terms of y, when I differentiate it, when I differentiate this, I just get this back, right? I just get that back. And when I differentiate these terms, I get back that, correct? Okay, yes. And when I differentiate this, because it has no x's, it goes away. And so, in general, I could have picked up a y function. Okay, so let's keep going. So I also want to say that I have to integrate the second guy with respect to y. So the second guy with respect to y, e to the x plus x cosine y dy. Okay, so this is going to be y e to the x plus x sine of y plus g of x. Again, where did the g of x come from? Just like the h of y, it's just saying that there's possibly some other function. Okay. Well, when we look at it, we see very obviously that this and this match up, and this match up. And so the only, there is no other function in here that could be this. And there's no other function here that could be this, right? So you try to compare the two to see if you can find a function. You can't. So these both have to be a constant. So it can be any constant. So we'll just set it equal to 0. Okay, so we conclude that h of xy equals y e to the x plus x sine of y. Okay, so that was a pretty straightforward problem. Most of y'all did pretty good on this. So number 4 was the hard one. So let's get into number 4 real quick. Okay, so number 4, actually, the number 1 problem y'all have is you didn't actually read carefully. So if you did it incorrectly, the problem was easier, and if you did it correctly, it was extremely difficult. And I was only looking for you to get so far if you did it correctly, because it would require a lot of grit, a lot of mathematical grit. So anyway, let's do it. You need to integrate. You need to integrate this curve, some curve, any curve. C is any curve from 1, 1 to negative 1, 2. Okay, so that's really important that you read that stuff and don't just go to this, right? So the problem is students often like to take the equations and sort of mindlessly apply theorems. So we gotta break that habit. Okay, so the temptation is to go ahead and apply Green's theorem, right? So Green's theorem says that if you have a closed, right? If you have a closed curve, then so if you have closed gamma, then the integral of gamma p dx plus q dy is equal to the integral of the domain, which is bounded by gamma. So gamma bounds d. So like you have this, right? The shaded part is d, and the circle around it is gamma. Then the double integral of that, q by x minus p by y dA, you have this. Well, you're going to want to do something like this anyway. We don't want to use the fact that Green's theorem applies, because it doesn't. Why does it not apply? Well, it's not a closed loop because the start and the finish are different, so it's not a closed loop. But here's the catch. Though it's not a closed loop, we want to show that it's conservative. Because if we can show it's conservative, then we can apply the fundamental theorem of line integrals, which is very important also. It's the one-dimensional Green's theorem, right? Or they're really all the fundamental theorem of calculus, right? Green's theorem, Stokes' theorem, divergence theorem, fundamental theorem of line integrals. They're all the same thing. So how do we do that? Well, we're going to show that those partials are actually equal to one another. Okay, so del q by del x, this is going to be the partial of x squared over 2x plus, x squared plus y squared, and you're going to want to apply the quotient rule. So after you've successfully applied the quotient rule, you should get this. Okay, so that's good. Okay, so let's keep going. So if I do this, if I compute that derivative, let's see, so partial of y over x minus the partial of y xy over x squared plus y squared. Whew. Okay, so yes, okay, so I'm going to do just the tan for a second. We gotta free up some space. So I'm going to do just the tan for a second. So if I take the derivative of tan, arctan, y over x, by the rules in the back of the book, or you could say by Calc 2 that you should know, this is going to give me y over x squared times, now I'm applying, this is the chain rule, right? So taking the derivative of the inside with respect to y, I get 1 over x. So that's where this comes from. So what is this going to equal? Well, when I push x through, I get x and y squared over x. And then I'm going to multiply top and bottom of this by x. As such. And when I do that, I get x over, so I'm applying it to the whole thing, x squared plus y squared. Okay, so keep in mind that when I did del q by del x, I got 2x y squared over x squared plus y squared. Okay, so the derivative of del y of arctan y over x, in summary, this is x over x squared plus y squared. Okay, so because I have a limited amount of space on the board, I have to erase that. Okay, so now I'm going to take the derivative of the other guy. So partial of xy over x squared plus y squared this is going to be, again, you're going to apply the quotient rule. So by the quotient rule, this is x times x squared plus y squared minus xy times 2y divided by x squared plus y squared squared. So if you don't follow that, you can just pause the video and look up the quotient rule, and you'll see that that's exactly what it is. Okay, so remember, I have to get the full derivative of I have to get the full derivative of p. So it's going to be the sum of this, right, plus this. Okay, now this right here, this right here, I can multiply the top and the bottom by x squared, y squared, like this. Okay? Now remember, I'm actually subtracting those, right? Because p has the minus sign, right? So del p by del y is equal to del y of tan y by x minus del y xy x squared plus y squared. Okay, so this minus this, okay, when you do that, it's pretty clear that this and this are going to cancel, right? They absolutely cancel, right? They cancel. So what you're left over with is this, right? And that minus sign, because you're subtracting, is going to become positive. So this is going to be x, y, 2, right, y squared over x squared plus y squared squared. Hey, that is exactly the other thing, right? Okay, so even though the problem did not ask you to show that this function is conservative, you actually have to do it. You have to do it anyway. And the previous exercise was intended to get your, your brain sort of primed to think about conservative functions. So that is a conservative function. So, so f is conservative, right? So f equals little f for some f. Okay, now we need to actually do it. Do what? Well, we gotta find what the little f is. Okay, so we're going to take the second coordinate, and we're going to integrate that with respect to y, right? Because you have f is equal to del, so it's there. That's what I'm trying to say. So if q is equal to del y of f, then f is going to equal the integral of q with respect to y. Okay, so recall, or look at your paper, that q, this is going to be x squared plus y squared plus e to the y, 1 minus y dy. Okay, so we're going to do this in parts. I don't mean integration by parts, but I mean this part and then that part. Okay, so when I integrate x squared and x squared plus y squared, I'm doing it with respect to y. So the first thing I can do is I can factor out that x because it's constant as far as y is concerned. So this is going to be x squared 1 x squared plus y squared dy, and that's the form a squared plus u squared du. And so we're going to apply. It's actually equation 17 in the back of your book, but you should just know this from Cal 2. This is this bit right here. This is going to give us 1 over x arctan y over x. Again, this equal sign is true by equation 17 in the back of your book. Okay, so this is going to equal x arctan y over x. And when I integrate the second part, e to the minus, this right here, e to the minus y, 1 minus y dy, okay, this is e to the minus y, e to the minus y, dy. This is very straightforward stuff. So the first one is very, very obviously minus e to the minus y. That's just normal integration. This one is integration by parts. You can use a DI table. I taught that to you, but again, it's Cal 2 stuff. And for brevity, I want to keep this video under 2 hours. So I'm going to just show you what it should equal. So I'm going to carry that minus sign down. And doing integration by parts on that, I get minus y e to the minus y minus e to the minus y. Okay, and when you simplify this, you should get this, right? Because this and this are going to cancel, so you're left over with that. Okay, so the point is, if we combine those two facts, put it up here, you're going to get that that's equal to x tan y over x plus y e to the minus y plus g of x, right? What is that g of x? Again, we don't know, but we're saying it might exist, right? There might be some g. Okay, and why are we doing all this? We're doing it because at the end, we can apply the fundamental theorem of line integrals. Okay. Whew. Okay. This stuff is exhausting. Okay. So, f is also equal to the integral of p dx. Well, right, this is p, right? You have that first part of your equation. The arctan of y over x, xy over x squared plus y squared. Okay, I don't want to do that yet. That's gonna end up not being a problem. I don't actually need to calculate that second part. So let's focus on the arctan. So I will admit this is a tough integration to do. Now, you can either, I mean, you had a week to work on it. So if you didn't know how to do it, you could use like online integration calculators. Symbolab is a really good one. But honestly, if you do enough Cal 2, you come across some very weird substitutions. So here's the substitution you actually have to do. It's very weird. So you're going to say, let u equal arctan of y over x. Very, very weird substitution. So du prime, or I should say u prime, what prime is that with respect to? It's actually u with respect to x, right? So, because remember, the differential is with respect to x, so again, that derivative needs to be with respect to x. I'll just go ahead and erase that. Well, what is that? Well, it is minus y over x squared plus y squared dx. Okay, so you should be able to see that just by thinking back to the integral of this, right? So if you integrate this, it should take you back to that, right? So it should make sense. Okay, so the other thing I want to say is that v prime equals 1. So what am I doing? I'm doing integration by parts, right? So this is the integral of u dv, right? This right here, right? And then I'm going to say this is u v minus integral v du. And if there's a 1 here, because this is u, right? If v prime is 1, sorry, I think I mean dv is dx. That's what I mean to say. Or you could say v prime is dx. Same thing. But not just 1, but dx. So when I integrate this, I get v, and I get x. Okay, so what does that mean? Well, it means that when I integrate this, I get u v minus v du, which is minus, right? So v du, so there's that minus here, so I'm going to write it up here, right? X, y, minus. So I'm going to go ahead and erase that, just put the plus here, divided by x squared plus y squared dx. Okay. Well, why does that help us? Well, keep in mind, I got to integrate this whole thing right here. So this right here is also right here, right? And because the integration operator is linear, when I integrate this, and when I integrate this, I pick up the negative of that right here, and I also pick up this. So the takeaway is that actually, when I integrate this is going to go away, because it's going to cancel with this, right? So all you're left over with is that. That's all you're left over with. Well, what is that? That is x arctan y over x, okay? And we have possibly some other functions in terms of y. Hey, that is perfect. Why is it perfect? Because look, these match up. So there's no other g of x, but there is an h of y. So you actually have to do the full calculation, right? So you see that g of x is equal, by comparing them, you see that g of x is equal to 0, and h of y is just y e to the minus y. Okay, so therefore, f of xy, our function, this is x arctan of y over x plus y e to the minus y. Okay, we're still not done with this problem, actually. It's a very long problem. Well, remember, we wanted to compute the integral of f of c, integral of f dot dr, right? That's what we wanted. It wasn't written like that. It was actually written as p dx plus q dy, right? I've just rewritten it. So this capital F, now we can rewrite it as a del f. Yes, del f dot dr. And this is where the magic comes in. This is by the fundamental theorem of calculus, we can say that this is just equal to del, you drop the del, and you say this is f RB minus FRA. Well, what is RB and RA? Well, this is the initial and the final point. Right? But what is the final? What is the initial and the final point. Well, RV, that's the final point. That's minus 1, 2. RA is 1, 1. Right? Now, does it matter? Does it really matter what curve we use? No. I mean, that's part of the hint, right? Because it says C is any curve, right? So when you apply the fundamental theorem of line integrals, you don't actually care what path you take. Okay, so you just care about the endpoints. So when I plug that in, I want to say f of RB, that's minus 1, 2, and then I subtract f of 1, 1. Okay, so just by plug those values in. Okay, so minus 1 times tan of 2 over minus 1 plus 2, right? 2 times e to the minus 2 minus arctan 1 over 1 plus 1 e to the minus 1. Okay? Well, what is that equal to? This is going to equal 2 over e squared plus 1 over e minus pi over 4 plus arctan of 2, and this is approximately equal to 0.96. Okay? It's about 1. This whole thing was just a really fancy estimation of 1. Okay, so that's it for that exercise. Problem 5. Ooh. We're almost halfway, so let's keep doing it. Let's keep going. Problem 5. Problem 5 says use Green's theorem to find the area. So this is 5. So area between the ellipse and the circle x squared plus y squared equals 1. So a quick comment. Every circle is a special type of ellipse, right? And what do we have here? Well, I can rewrite this as x over 3 and y over 2, right? Y over 2. And so that's going to tell us that your ellipse has, the y-axis, it's going to meet the y-axis at y equals 2 and minus 2, and x equals negative 3 and 3. And then for our other guy, right, our circle is going to be in the center, and we want to find this area here. Okay, so we want to find the total area minus the inner area. Okay, now remember I just said that a circle is a special type of ellipse. So all we got to do is find the generic area of an ellipse, and then subtract these two ellipses' areas from each other. Okay, so there's actually an example from your book. It tells you how to use Green's theorem in this exact setting. So so if you want to find an area, so the area is the area of a domain is the double integral of that domain, right? Like this. Right, so there's this 1 hiding here, right? And I want to use Green's theorem, so I want to say that's del q by del x minus del p by del y. For some sort of vector field, f that has components p and q. Okay, we're not saying there's various sorts of vector fields you could use, right? But the most natural one would be let p of xy equal 1/2 y, and let q of xy equal 1/2 y. Okay, so if you just pause the video for a second, take the take the derivative of this with respect to y, take the derivative of that with respect to x, okay, perform that calculation, you'll actually see that that's equal to 1. So if you need to, go ahead and pause it for a second, just verify that, okay, so you do see that it's equal to 1. Okay, so because it is equal to 1, I'm now going to continue with my calculation. So well, what do I want to say? Well, I want to apply Green's theorem, right? So what does Green's theorem say? Well, it's actually going to say this. 1/2 y dx plus negative 1/2 x dy. Okay, that's what it says. Now in the book, the way they write this is 1/2 x dy minus y dx. Okay, so that's how they write it in the book for this very specific example, because it's neater. You know, we like our, we like writing things a certain way. Oh, yes. Sorry, I wrote that wrong. There should be a minus sign here, and that's a plus sign. And then when I move that over here, that's how that goes. Okay, so what is x and y? Well, for a generic ellipse, it's going to be a cosine t, and y equals b sine t. Okay, so what are a and b? Well, a and b in our case are 3 and 2. Okay, 3 and 2. So go ahead and copy that down. I'm going to erase it, and right, so you should have 1/2 c x dy minus y dx, and this is going to equal 1/2 0 to 2 pi. Okay, now I'm just going to directly apply those, right? So I get 3 cosine t, 2 cosine t dt plus y, which is 2 sine of t. Take the derivative of it. Take the derivative of x, right? So the derivative, so you get a minus. You have a minus here because that's what we were told to do, is subtract. So you put the y in there, which is minus, which is 2 sine t, and then when you take the derivative of x, that's negative 3 sine t. Okay, so you pick up that negative, and then 3 sine of t dt. Okay, so we can factor out 3 and 2, which is actually a and b. Okay, so it's a and b over 2, integral from 0 to 2 pi, And this is cosine squared plus sine squared, which is just 1. So that's dt. And so that's the generic area for an ellipse. So from the first, so we want to compute this. So this is going to be the entire ellipse minus the inner ellipse, right? Okay, so it's obvious, isn't it, that what we want is this ellipse, which is from here, it's going to be 3 times 2 over 2 times 2 pi, which is from this integral right here, minus 1 and 1, right? So 1 times 1 over 2 pi, right? And this is going to give us 6 pi minus pi, so that's 5 pi. Okay? So your final answer should be 5 pi. Hopefully that makes sense. We're just about at the 1 hour mark, and I have lots of energy, so I'm going to keep going. Okay, so problem 6, this is a nice, neat problem. So problem 6, this asks us to prove that a certain vector field is not the curl of any other vector field. Okay, yeah, you can see that. Okay, so you have fxy z equals e to the x y z x z squared. Okay, so we want to show that this is not the curl of another vector field, right? So not show f is not the curl of another, right, vector field. Okay, so this is very easy. So we do what's called a proof by contradiction. So the idea is you actually assume it is possible. So you say, actually, sir, you are wrong. This is the curl of another vector field. So we say, suppose f equals the curl of G, right? So G is some vector field. Then, what do we have? We have 0 equals the divergence of the curl of G. Now, where did I get this? This is just right out of your book, and you can show it. So you can just sit down, you can show it. It's very simple. It's going to follow from the fact that with sufficiently smooth vector fields, mixed partial derivatives commute, which means that the partial of y followed by the partial of x is the same thing as partial of x followed by partial of y. Okay, so, and this is going to be true for any x, for any y, and for any z. So for any x, y, and z. Meaning that it's equal to 0 everywhere. Okay, so curl of G is equal to f. So this is like that, right? And what is the divergence? Well, the divergence is, it's this. So it's the sum of the derivatives in order. Okay, so this is that, and that is such. Okay. Now keep in mind, I said it's for any x, y, and z. Okay, so some of you said that, you know, from here, you said, well, this is clearly not 0. Well, it's not obvious to me that you can really see why it's not equal to 0. So let's go ahead and let's say that you have e to the x equals negative z 1 plus 2x. Okay, so I just moved this to the other side, and I pick up a negative sign. Okay, so I said that this is true for any x, y, and z, so let's actually pick an x and a y and a z. So how about let's let y equal 0, or whatever, because y doesn't show up. Okay, so we'll let z equal -1, and we'll let x equal -1/2. Okay, so if x equals -1/2, y equals 0 and z equals -1, then we have that the right-hand side is equal to 0. So the minuses cancel, but when you plug in 2 times -1/2, you get -1, and 1 minus 1 is 0, so the right-hand side is equal to 0, so you have 0, but the left-hand side is e to the minus x, e to the -2, e to the -1/2, sorry. So the point is that this is clearly false. Now, just, keep in mind, we're not saying that it's equal to 0 for some x, y, and z. We're saying it is equal to 0 for all x, y, and z. So it just takes one x, y, and z set of x, y, and z to falsify that statement, just like that other problem earlier that I was working on. Okay, so that's pretty much it for that. The next problem is one of my favorite problems. I have asked it literally every semester since I've taught at St. Tom. Right. So you have a surface, okay, and you can't see that surface. Let me draw it with another pen. All my pens are running dry. Okay, so you have some surface, and you want to find a tangent plane at a point. And this point is 2, 1, 3. Now, to find a tangent plane, let's think back to our early days, where we actually had tangent planes, and we want to find a normal vector. So the way we did that, if you had, let's say you had here's a plane, right? So any vector on this plane is tangent to this plane, kind of obviously, right? So let's say that we have this vector here, and it passes through a certain point, and then I attach this other vector here, and let's say they're linearly independent. Then by early semester stuff, you take the normal vector, and that normal vector is tangent to that plane at that point. So the idea is that if you have a pair of vectors that are tangent at the point, then by computing their cross product, you can get the normal. So we don't have a tangent plane, but we want to find a tangent plane. So the way we did it was we took those tangent vectors. Okay, so what is our tangent vector? Well, we have a curved surface, and we just think back to our Cal. Everything is about Cal 2. If you understand Cal 2, it's very helpful. So think back to Physics 1 and Cal 1 and Cal 2. If you have a curve going along the surface, the derivative of that curve is always tangent. It's always tangent at every point. So if you want a pair of vectors that is tangential at a point, simply draw two curves, right? Draw two curves through here, and then find their tangents. So right, so here I have my curved space, right? And so I have my derivative vector here, and I have a derivative vector along this curve. See how the vector changes? And for this one, it doesn't really change, right? But for this one, It does. Okay, so that's all fine, but let's actually do the calculation. So remember, the drawing here is our parameterization, some curve. Well, hey, guess what? We're actually given two curves. So we have a pair of curves. We have R2 and R1. And R1 is equal to 2 plus 3t, 1 minus t squared, and 3 minus 4t plus t squared, while R2, I use the variable u for that, and that is 1 plus u squared, 2u cubed, minus 1, 2u plus 1. Okay, well, the first order of business is to find where the curves actually intersect this point. So for the first one, it is pretty clear that t has to equal 0, right? Because if t is equal to 0, you get 2, 1, and 3, okay? So you have t equals 0. For the second one, if u equals 1, then 1 plus 1 is 2, 2 minus 1 is 1, which is what we want, and 2 plus 1 is 3. So we want t equal to 0, and we want u to equal, sorry, we want t to equal, I'm not saying, the words are not coming out correctly, it's a long day. We want t to equal 0, we want u to equal 1. Okay, so now I'm going to compute the tangent vector at every point by computing the derivative of this curve. Same thing. Okay, so the derivative of this is 2 plus 3, sorry, just 3, 3 minus 2t and minus 4 plus 2t. And then the derivative of this with respect to u, right, the derivative of that with respect to u is going to be 2u, 6u, and 2. Okay, now, here's the thing. We computed t equals 0 and u equals 1 for a reason. We need to plug them in to this equation. So if I plug in t equals 0, that's going to make this go away because it's 2 times t, and t equals 0. So that's 0. Okay? And then here, that's also going to go away because that's 0. Okay? So in summary, you get R1 prime of 0 equals 3, 0, and 4. 3, 0, and negative 4. You get negative 4. Okay, and R2 prime of 1, when I plug in 1, I get 2, 6, and 2. Okay, so now we need to find the normal vector, right? So, because the derivatives of these vectors both lie in the same tangential plane, the normal vector, the vector normal to both, the vector perpendicular to both of them is just that normal vector. So if we can find the vector this way, the cross product, right, that's going to give us our plane. Okay? So what is that very precisely? Well, that is R1 prime 0 cross R2 prime 1, which is ijk 3, 0, minus 4, 2, 6, 2, and you should get 24 minus 6 plus 8, comma 18. Okay, and so this is going to be 24 minus 14, 18. Okay, so go ahead and pause that video and check it for yourself, do the calculation. Okay, and once you have that vector, we're going to call that n, because that's our normal vector. Okay, so you have that. Let's erase it. Okay, so now we're going to use that vector n, which is 24 minus 18, sorry, minus 14, and 18. And remember, we want to get the plane that goes through that point. So that's going to be 24x minus the point, which is 2, minus 14, y minus the point, which is 1, plus 18, z minus the point, which is 3. And after a little bit of work, you should get that. And it's like no work at all, right, compared to what we've done so far. Going from here to here, it's nothing. Okay, so we are making some progress. Okay, so problem 8. Problem 8. Okay, problem 8 is fun. Okay, so problem 8 says evaluate, so evaluate the integral of of 1/2 y squared dx plus z dy plus x dz, right, where C is the curve of intersection of the plane x plus z equals 1 and the ellipsoid x squared plus 2y squared plus z squared equals 1. Okay, oriented in the clockwise direction from the origin. Okay, so what does that orientation thing mean? Just don't worry about it for now. Okay, so I think it's helpful to actually draw this. Okay, so what you do, the way you draw an ellipsoid is you consider all of the points other than the one you're interested in. Okay, so if you want to know where x, you want to know where the principal points of intersection are, and then we can connect all of them. So it's that y and z equal to 0, so that had to be that x is equal to 1. Okay, and then if x and y, or sorry, if z and x are 0, then y has to equal, or y squared has to equal 1/2, right? And if y has to equal, if y squared has to equal 1/2, then y has to equal 1 over the square root of 2. So 0, 1 over the square root of 2, 0, and this is 1, 0, 0, and it's going to basically look like this, right? And then we have that part in the z direction, right? So if those are both equal to 0, then z is equal to 1. So then it's gonna go up. So it's gonna look kind of like this. Okay. Okay. So it's basically like a bullet or like a football. Okay. Now we have this x plus z equals 1. Okay, so x plus z equals 1, that's z equals 1 minus x. So it's basically going to cut like that, right? And so you have this plane cutting. And that's when you look at it and you say, I have no idea what that looks like, what that intersection is. Okay? That's okay. Well, to find out the actual intersection, what you're going to do is you're going to plug this into that. So let's go ahead and do it. Okay. So I'm going to put that on the slide. Okay. So you have z equals 1 minus x. Okay. So I shouldn't say let z equal 1 minus x, but it's more like observe when they intersect, z is equal to 1 minus x. That's what I mean. Okay, so the ellipsoid is, I guess I should always write in red. So the ellipsoid is x squared plus 2y squared plus 1 minus x squared, 1, right? Because that's z, right? That's z. And so when I solve this, I get x squared plus 2y squared plus 1 minus 2x plus x squared equals 1, and then that's equal to 2x squared plus 2y squared minus 2x equals 0. And if I divide everything by 2, I get x squared plus y squared equals x, right? So that's fine and dandy. You can also easily show, okay, so we're going to want to use this, but we're also going to want to use this fact right here, is that it's also equal to this equation. Okay, so it's equal to this, x minus 1/2 squared plus y squared equals 1/4. So to get that, you drop the 2's, right, and then move the x over there, okay, and then move the y over there, and then you just think really hard for a second, and then you get this equation. Okay, that's all. And why is that useful? Well, it's useful because we know that it's a circle of radius, well, this is 1/2 squared. So it's a circle centered at 1/2, 0, because of this, right? So the center for x is 1/2, and the center for y is 0. So it's going to be centered here, and it's got a radius of 1/2. So that's really neat, because that means that it's this, right? So that's the equation of their intersection. Okay, and we're not even worried about this. We're not even really thinking about z at this point. It's just x and y. Of course, what is z? Well, it's 1 minus x. But so when you press it down, when you project it into the plane, it's just this. It's just that circle. So the intersection between this plane and this three-dimensional ellipse called an ellipsoid, excuse me, it's very weird because you take a three-dimensional ellipse, you intersect it with a plane, what do you get back? You get a circle. That's absolutely madness. Okay, so let's go ahead and do this calculation. So, okay, so this is equal to the integral of c 1/2 y squared zx dot dr, okay? So all I did was say that that's p, q, and r, right, for some vector field, p, q, and r. And I rewrote it like this, right? So dx, dy, dz, you just rewrite that as dr, okay? Now, by Stokes' theorem, right, by Stokes' theorem, this is equal to the curl of this dot ds with the dollar sign, because that's what I like to use. And I'm going to go ahead, You can go ahead and, I need to erase this for some space, but just keep that in the back of your mind. Okay, so what is this equal to? Well, precisely it's equal to this, right? This right here. So 1/2 y squared z and x dot ds, right? And then when I do this calculation, what do I get? Well, you get -1 minus 1 minus y dot ds. Okay, so just go ahead and pause the video and check it out. Okay, so you've done that. We'll just verify it. So this and that gives us 0, minus 1, right? This and that gives us 1, 0, but then you always negate the second one. And then finally, this and that gives us 0, minus that. When you take the partial of this with respect to y, the 2 comes down, they cancel, and you just get a y. But you're subtracting, so you get negative y. Okay, so what now? Well, I need more room, so I'm going to say this is equal to the double integral -1, -1, negative y dot ru cross rv, sorry, rx ry dA. Okay, so what is rx and ry? Well, that is the position vector, right? That's the position vector on the intersection, on the surface, right? This S is the surface of intersection between the plane. Sorry, it's the intersection of the plane and the ellipsoid is a curve, which is given by a circle, right? We did that earlier. But the space between that curve, so you have a circle in space, the stuff between it, that's S. Okay? But let's keep in mind that, so you want to note this. So note that everywhere, right? Everywhere on S, we are on x plus z equals 1, right? That's just a fact, because if you're intersecting this with an ellipsoid, in particular, you're still on that thing, right? So you have this ellipsoid, and when you find the intersection, you have this curve. That curve bounds the, right? So I have a curve between this plane and some football. Well, what's the stuff inside that curve? It's more of the stuff that you start off with, right? So even though you're intersecting, when you intersect, you lose the stuff on the inside because it's intersecting with an ellipsoid, and you're just looking for the curve. You get it back, at least the part inside the ellipsoid, which is S, you get it back. So you're still on x plus z, but when you're on x plus z, well, you still have z equals 1 minus x, okay? So x, y, r is the function of x and y. That's the point, and you still have this constraint. So what is x? Well, x is x, and what is y? Well, y is whatever we need it to be to keep inside that ellipsoid, but the really cool thing is that z is 1 minus x, okay? Forget about the ellipsoid for a second. You're still on the plane, so that is still true. But if that's true, then you have r of x, xy, is going to equal 1, 0, minus 1, and r of y, xy, is going to equal 0, 1, 0. Okay? And when you compute the cross, it's very simple. So r, x, xy, cross r, y, xy, this is going to equal I, j, k, 1, 0, minus 1, 0, 1, 0. So this is just equal to 1, 0, 1. Okay, I mean, and it's really obvious, right? Now, some of you are gonna use the other formula where you have dot in. So there's that other formula where you say s dot ds equals, right, integral s f dot in ds, right? So $s. Now here you have n. What's the thing about n? Well, n is a normal vector, a unit normal vector, normal to the surface. Well, obviously the surface is this, and so again, it's utterly obvious, right? What is normal to this? Well, it's 1, 0, 1. Okay? That's what you got. But you need to normalize it if you're doing n. Okay? So now you divide it by the square root of 2. Perfect. What's the problem? Why didn't I do that? I'll tell you why. You got to use this ds. You still got to integrate over using the ds differential. I don't like doing that. It's not good. I'm going to use dA. You can do it. It's more complicated. You're going to have to work really hard just to get back to this right here, which we can handle. Okay? So to summarize, I'm going to integrate over s, minus 1, minus 1, minus y, and I just computed. So the point is don't do that. Do it this way. So I get this, and I get 1, 0, 1 dA, and now I simplify this as s minus 1 minus y dA. Okay, so what is s? Think back. It's this circle, right? It's that circle. And now we're going to compress it. We're going to project it down, right? We project it down. Crap. This should have been a D the whole time. Okay, so just go up. The whole time, that should have been a D. Which was the whole point of what I was saying, right? So the point is that if I go up here, right, I have s minus 1 minus y dot ds, right? I go from here to here, right? So that's just one form of the equation. From here to here. That's how we want to do it. Okay, so now that I've done that, I have d, I know what that is. So it is, well, from the picture, what is theta? So I start down here, right? I start down here and then I go up, right? So the south end is negative pi over 2 and the north end is pi over 2, right? So I start here and then I go all around. So it's minus pi over 2 to pi over 2. Okay, so minus pi over 2 to pi over 2. What about r, right? So the way to think about this, the correct way to think of it, is that whatever angle you're at, if you're, say, at that point, r is going to go between here and that point, right? Here and, say, this point, right? So that's, the outside integral is with respect to theta. Well, what was our equation for this circle? So I want to go from here to the circle. I want to go from, again, I want to go from the origin, because I'm extending r. So I go from the origin to the edge of the circle. What is the circle? Well, this circle is x squared plus y squared equals x. Right? Okay, well in polar coordinates, this is going to be r squared, and this is going to be r cosine theta. So I'm going to divide by r, and I just get r cosine theta. So the circle is just r equals cosine theta. So I want to go from r equals 0 to the circle, cosine theta. So this will be cosine theta, and this will be 0. And this will be r sine theta. R dr d theta. Okay? R dr d theta. Okay, so once you have this set up, this is not a lot of work, but let me just say, if you do it correctly, you should get, oh, what the heck, let's show the whole thing. Why not? So this should equal minus r plus r squared. I think I may have written cosine. It should have been sine because I had y, and y is equal to r sine theta, not cosine. So if I wrote cosine, apologies. So sine theta, dr d theta, and the bounds, and so this is going to be minus 1/2 r squared plus 1/3 r cubed sine theta. Yes, sine theta. R goes from 0 to r equals cosine theta. I think that was the cosine I was thinking of. D theta. Okay, now I'm going to plug in that value for r, so I should get minus 1/2 cosine squared theta plus 1/3 cosine cubed sine theta d theta. Okay, so pretty much done. See, so I'm going to rewrite the cosine squared using what's called the half angle formula. So first I'm going to factor out this minus. So I get minus 1/2, pull that out, and then you're left over with the cosine squared. Cosine squared you can rewrite as 1 plus cosine 2 theta over 2 d theta. Okay, what about this guy? Well, this is going to be 1/3, and you're going to integrate from 0 to 0. And you have u cubed du, because u is equal to cosine theta, so du is minus sine theta d theta, right? So u du, and when I plug in negative pi over 2 into cosine, I get 0. When I plug in positive pi over 2, I also get 0. Or another way of saying it is, you don't even need to know what the value is. You just know that you're using cosine. Cosine's an even function, and since those are the same number off by a minus sign, when you put them into cosine, it's gonna evaluate the same thing. So basically, that second term is just gonna go away, and this is going to give us negative 1/4 theta plus 1/2 sine 2 pi. And theta is going to go from minus pi over 2 to pi over 2. And after you just crunch the numbers, you should get minus pi over 4. Okay, so do make sure you get that. But that's basically it. Okay. So that was problem 8. We're going to keep going. Problem 9. problem 9. So problem 9 says, let C be a simple piecewise smooth curve, which is sufficiently smooth, that lies in a plane with a unit normal vector ABC. Okay, we want to show that the area enclosed by C is some value. Okay, so the idea is you have a plane. Okay, so it's constant. It has constant curvature. It's flat, and you have some curve C, and it's got a normal vector, and that normal vector is A, B, and C. I don't know if you can see the pin. Let me use a different color. You have N equals A, B, and C. Okay, so what we want to do is we want to show that 1/2 of, this is C, curve C, 1/2 of BZ minus CY dx plus CX minus AZ dy plus AY minus BX dz. We want to show that this is equal to the area inside this curve. Okay, it's actually a very easy problem. You might want to think about area formulas or whatever, but don't do that. Just start with this. It's the most natural thing. Start backward. Okay, so what is this equal to? Well, got this 1/2, so I'm just going to write that 1/2. Okay, and this is going to equal F dot dr, where F is equal to the vector field. F has parts x, y, and z, so it's equal to BZ minus CY, CX minus AZ, and AY minus BX. Okay, so literally all I did, right? All I did is just take those parts, that's P, Q, and R, and I just wrote it right here, right? P, Q, and R, right? Okay. Like that. Okay, great. So what is this equal to? Well, it's equal to, by our favorite theorem, by Stokes' theorem, it is equal to that, right? Well, what is the curl? So it's 1/2 double integral of S curl. This is going to be I, J, and K, del X, del Y, del Z, and I'm going to write BZ minus CY, CX minus AZ, AY minus BX. Okay, and now it's just very routine calculation to show that this is 1/2 double integral S to, let's see, you should get 2A, 2B, and 2C. Okay? Don't forget your dot ds. Okay, so let's see that that's true, right? So when I take the derivative of this with respect to y, I get an a. When I take it with respect to here, with respect to z, I also pick up an a. So that's 2a. Okay. Now this with respect to x, I get a b. Now this with respect to z, I get a b. So 2b. The final one, this right here with respect to, this right here with respect to x, I get a c. This right here with respect to y, I get a c. So that's how I get the 2c, 2a, and 2b. So that's right here. Okay. So let's keep going. So I can factor out that 2. You just factor it out because that's how numbers work with vectors. You just factor it out. So the 2 is going to go in the front. So you get 2, and those are going to, they'll cancel. You get ABC like this, dot ds. Okay, well, what can I say about this? Well, this is going to equal, the 2's are going to cancel, right? Think back to your other definition. This is dot in ds, right? This is just the definition of dot ds dollar sign, right? So there's kind of 2 different ways to work with it. One, you get the f with the ru cross rv, and the other one you get the in. But what is in? In is just ABC, right? So this is just s ABC dot ABC, right? Or I guess I should write it like this. Let's write it like this. Okay? But what is in dot in, right? So in dot in, another way of saying that is this, right? So if you take the dot of 2, if you take a vector and dot it with itself, it's the same thing as the norm of the vector squared, okay? But we also said that it's a unit normal vector, in particular unit, emphasis on unit. And what does unit mean? It means that the norm is equal to 1, so this is going to be equal to 1 ds, and anytime you integrate a domain, you just pick up the area. So we're literally integrating S, just the surface S. So this is going to equal the area of S. Okay, that's what we wanted to show. So this is a correct proof. I saw a lot of really, let's call them proofs, but not proofs. Okay, so that's it. Number 10 is just loads of fun. I love it. So let's get right into it, and that'll be the end. So, so 10 is starting to get into some higher level mathematics. Looking for my eraser. Here we go. Okay. Well, it's getting into higher level mathematics, but actually deriving it is very simple. Okay, so you have f dotted with g equals f dotted with nabla g plus, I think I need some light. Okay. There we go. Yes. Okay. So, yes. G dot del f plus f cross the curl of g plus g cross the curl of f. Okay, so before I go full metal and solve this, one thing you should note is that f times g is the same thing as g times f for vector fields, right? And f has components, and it's a function of x, y, and z. So f times g with x, y, and z, this is just equal to f x, y, and z times g x, y, and z. Okay. If this doesn't make any sense, just think how do you multiply a pair of functions f and g, right? You just f of g of x is just f of x g of x, right? Same thing. That's literally all I mean by that. Nothing too complicated. And your book says that, and it's also the most obvious thing to guess. Okay, I mean, if you just read the chapter, it's in there. It's in there, I promise. Okay. So, I'm going to work on the right-hand side. Okay, so we're going to say, suppose F equals P, Q, and R. And G equals A, B, and C. And each of these are going to be functions of x, y, and z. Okay, so A is a function of x, y, and z. B is a function of x, y, and z, and so on. And of course, nabla is the vector operator of partial of x with partial of x, partial of y, partial of z. Okay, so that's what that is. Okay, so getting right into it. So f dot nabla. I'm gonna do the first term first, right, and then I'll do the second and so on. So f dot nabla g. This is gonna equal, okay, p, q, and r dot partial, 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 right, a, b, c, right, because g is a, b, c, okay. And now I'm just going to multiply those together. It's important to keep the order in check, right? So p times that, not the other way around, right? Because the order for that actually does matter. So you should get p like this, q del y plus r del z. Then you get a, b, and c. And now you're going to apply each of these to this, right? Now the p's and the q's and the r's, you're going to treat those like constants. But when you multiply this by a, you'll see what's up. So this should give us p del x a plus q del y a plus r del z a, right? So that's the first component, right? So I just applied it to the first component. Now I'm going to apply it to the second component. So I should get p del x b plus q del y b plus r del z b. And then finally I apply the third component to the c. Or sorry, I apply the whole thing to the third component. So I get p del x c plus q del y c plus r del z c. Okay, so you should have this vector of three components, 1, 2, and 3, and it looks like that. So I'm going to give you a moment to write that down, and then I'm going to erase it, okay, and then I'm going to rewrite it in a certain way, okay. So fortunately for you, you can rewind if you want. Okay, so hopefully we'll finish before the 2-hour mark. So this will be p dot del g. This is going to be p del x a plus q del y a plus r del z a p del x b plus q del y b plus r del z b. Okay, I'm going to keep going. P del x c plus q del y c plus r del z c. Okay, so you might say, well, okay, great. Now I got to do this one. I am so tired. I don't want to do it. Don't give up yet. Okay? Just swap F and G. So every time you see a P, put an A. Every time you see a Q, put a B. Every time you see an R, put a C. Okay? So if you do that, you should get the following. Okay, so a lot of times mathematicians talk about symmetries. This is a type of symmetry where I just take all the letters and I swap them, and I get this other formula. This saved us a lot of time and a lot of brain energy. Okay, so the next thing I want to do is compute the curl of f and then take g cross that, okay? So from your textbook, you have that the curl of f is just, I'm not going to even do the calculation you need for curl. It's nabla cross f. I'm not going to do that. I'm just going to copy the definition straight from the book. Okay, so what that is if I have g, so this is going to be g cross the definition of the curl. And what's the definition of the curl? It's del y r minus del z q del z p minus del x r minus del x q minus del y p. Okay, so that's literally just the definition. So now I'm going to apply the definition of the cross, right? So when I apply the definition of the cross product, I get I, J, and K, and G, remember G is A, B, and C. And so because that's equal to A, B, and C, I'm going to copy these parts here, and that's going to be this right here, okay, ZP minus del XR del Q minus del YP. Okay, and now I'm going to do the fun part of writing out what this is if you did your calculations correctly. So, well, what is it? Well, it is B times del XQ minus del YP minus C del ZP minus del XR. Where was I? Second one, R, okay. C y r del ZQ minus A del XQ minus this y, and then so that's the second coordinate, right? And then the third coordinate is going to be A del Z P minus del X R minus B del Y R minus del Z Q. Okay, so that's like a real pain in the butt, but you can do it. Okay, so once you do that, you're gonna add. You're gonna rewrite this. Okay, you're gonna take that. You're gonna rewrite this stuff down here, and you're again gonna switch A's for P's, B's for Q's, and C's for R's. And then when you do that, you should get this sheet right here, which is, I wrote this. This one's really neat. So this is what you should get. Go ahead and pause it. Just go ahead and look at that. Pause it. Okay, so after you've copied it, maybe you copy it down. So how did I get this first section? That first section, I literally just add up this, and then this coordinate right here with G and F switched, right? So when I add them all up, right, I'm just looking at the right-hand side. So when I add them all up, I get this. Now, the highlighted bits are those things that cancel, right? Do you see how those cancel? Okay, so what do I get left over with is, well, it's strangely enough, you get P del XA and A del XP. Well, guess what? That's the product rule applied to P and A, right? So this term and this term, I can just write that as the derivative of PA with respect to X. And then again with Q and B and R and C. And so that tells me that the that's actually just F times G, but taking the derivative of it with respect to X, right? That's just the first coordinate. It's F times G, taking the derivative F times G with respect to X. And if you do it all three times, you know, for the second coordinate, you get the same thing, but this time you get the derivative with respect to Y. And then in the third coordinate, you're going to get it with respect to Z. Okay? And that tells us that right-hand side is equal to the first coordinate is going to be equal to the derivative of F times G with respect to X. The second coordinate is F times G, taking the derivative of that with respect to Y. And the final coordinate is the derivative of F times G with respect to Z. But that is just the gradient of F times G. And that proves the results right there. And that concludes exam 3. And it's been a true pleasure teaching you this semester, and I wish you the best of luck. And enjoy your summer, and good luck on your final. Feel free to contact me in the future. Take care.